Okay, so in this problem we have the 5 compounds together in one mixture, and we want to separate them. We have access to water, ether, hydrochloric acid, and sodium hydroxide. If we add sodium hydroxide, we make the pH of the water higher, and if we add hydrochloric acid, we make the pH of the water lower. What happens is when we change the pH of the water, some of the molecules will become charged or polar, and some will become not charged or non-polar. When a molecule is polar, it's going to dissolve in water, and when one is not non-polar, it's going to dissolve in ether. So first we can just add ether and water to these two, to the first mixture, and I'm going to make the pH of the water 2. What's going to happen is the pH of the water is 2, so the solution is acidic. It's more acidic than all the other compounds, so it's going to remain in its respective form. On the left side, anything that is polar is going to fall in water. Anything on the right side that is nonpolar is going to go into ether. So let's start with the water. Polar molecules. The only polar molecules we have are the ones with the NH3 group, which have a charge. So we're going to draw first one, NH3 plus, and it has double bonds. So because it's polar, falls into the water. And the other one is almost the same molecule except without the double bonds. It has a charge. So because they're charged, they fall into the water. On the right side, the non-charged compounds are the ones with the COOH group. And this one does have the double bonds. The next one is the OH group. It also has double bonds. And the final one is the chloro group. So these fall into ether because they're not polar. They don't have the positive charge or the negative charge. Okay, so now if we look at the compounds on the left side, both are polar, and the only difference is the pK. To get them separate, we have to change the pH of the water. So first we're going to add ether and water. And if we change the pH of the water, we want one to be acidic, and we want one to be polar and one not to be non-polar. So we change the pH to, let's say, 2. The two compounds will remain in their acidic form, so they'll remain charged, so that can't work. If we change it to a pH of 13, the pH of the water is really basic. The two compounds will want to donate the hydrogens, but because both donate, they'll become nonpolar, and again, we want to separate them, so we only want one to be nonpolar and we want the other one to be polar. So the best thing to do is to make the pH around 7. And 7 because one of the compounds will donate the hydrogen and the other one will not donate it. So here on the left we have water, and on the right we have ether. So let's look at the first compound. The pKa is 4.6, lower than the pH of the water. Because it's lower and has a difference of 2 in pH, the compound on the left will donate the hydrogen. So on the left we have NH2. So the compound on the left will donate its hydrogen, making it NH2. And because it donated it, it's no longer polar. It has no charge, so it's going to fall into the ether. The other compound with the 10.5 has a higher pK than the pH of the water, so it won't donate a hydrogen, leaving it in its form as it is currently, so it will be NH3 plus. And that's how we separate those two compounds on the left. Okay, so now if we look at the right side with the 3 compounds in ether, all of them are nonpolar. We want to make some of them polar and some of them nonpolar. So we're going to change the pH of the water while adding ether. We can make the pH of the water 2. If we do that, the first two compounds, the COOH and the OH, won't be able to donate their hydrogen because the solution is more acidic than those two compounds. So if we go the other way where the pH is 13, that will work. It's going to separate the two compounds from the Cl. Instead, though, I'm going to make it a little bit with more practice, so I'm just going to make the pH of 7. So on the left side we have our water, on the right side we have our ether. On the left side we have we're going to have our polar molecule. The COOH compound, that one is more acidic than the water solution, which has a pH of 7, so it's going to donate a hydrogen, causing the compound to become polar. So what we end up with is with a COO minus. Because it has a minus, it's charged and it goes into the water. The second compound, the OH group, that one has a pK of 9.95, and that one is more basic than the water of the solution, so it can't donate a hydrogen. So it's gonna remain the same. We have the OH and the Cl. The Cl is really basic, so it's not really going to change. And it has no hydrogens to donate, so it's not really acidic either. Now we have those two, these two together, and we're going to add more ether and water. And separate it, we can only make the OH group polar by making the water really basic. So if we make the pH of water 13 or higher, 14, 15, it's going to make the OH group donate the hydrogen. So on the left side we have water. The compound will donate a hydrogen, leaving it O minus, which is it has a charge, it'll fall in water, leaving the other one with a Cl. It's kind of bad, but I think you get the picture. So essentially, the way we started was we had the 5 compounds, and we wanted them separate with access to water, ether, hydrochloric acid, and sodium hydroxide. We change the pH of the water, and when we change the pH of the water, some molecules will become polar, some will become nonpolar, and that's going to make them fall into water or ether. And when we keep changing the pH of the water, we can separate it further and further, like we did. So hopefully this video helped.